Hello, and welcome to this presentation related to application of Macaulay's method for solving beam deflections of constant section simply supported beams. This presentation builds on two previous presentations. The first one introduced the Macaulay's method, the background theory, and the application of the step function method. In the second, we consider some numerical exercises, and in this presentation we're going to consider slightly more complicated numerical exercises. It's strongly advised that you've seen the two previous presentations before working through the contents of this presentation. Here's another exercise, exercise 5. A 16 meter long simply supported beam is loaded as shown in the question. We have 3-point loads applied here to the beam, and we have two partial UDLs over the beam. We're given in the question the Young's modulus is 205 times 10 to the 6 kilonewtons per meter squared. We're also given the actual beam section type, and that's a 686 by 254 by 140 kilograms per meter universal beam from BS4. So there's a table on the next slide we'll need to use to extract the relevant information. As always with these type of questions, we assume the self-weight of the beam is negligible, so it's ignored from the calculation. Just adds complication for no reason if we include it. So the question wants us to determine 1. The slopes at both ends of the beam and at 6 meters in from the right hand end of the beam. Just be careful there because our x dimensions are always measured from the left hand end of the beam. And as the total length of the beam above is 16 meters, then that will actually mean 10 meters in from the left-hand end of the beam. 2, the deflections at both the ends, which of course are 3 in this particular case, and at 6 meters in from the right-hand end of the beam. And part 3, if the maximum beam deflection is limited to a 200th of the span, and that's the distance between the supports in this case, we've got to select the smallest universal beam section that can be used from the extract of BS4, and then calculate the actual maximum deflection for the chosen beam section. Answers are shown in the brackets here. Exercise 5M continued. Here's our universal beam extract from BS4. Use an old version of BS4, it should be noted here. So we have a 686 by 254 by 140 kilograms per meter section. So in this table, it actually will provide us with the moment of inertia, or the I value. So I can see that is going to be 136,276, but that has the unit of centimeters to the 4, so I will need to convert that in a moment to meters to the 4. Also notice that the moment of inertia, or the I value we're considering here, is about the XX axis, that's this axis here, and that's the conventional axis we would try and bend the I section about because it's stiffest about the XX axis, so that's the axis we assume it's bending about in this case. And again, for reference, the moment of inertia in BS4 is actually the second area moment value, the I value, as far as we're concerned in our analysis. So we essentially have the E value, we have the I value. We can start the solution. Don't forget we will need to calculate the reactions. Again, there are 2 of them here. We need both of them in this particular question. And from there we'll have to calculate the differential equation of bending for our particular beam, working from left to right. We will integrate that to find the slope equation, integrate that to find the deflection equation. We'll have to then find our boundary conditions, which of course will relate to the reaction positions here. Solve for our constant of integration, and then we've got our equations we can use to start solving the particular problem. One point to notice, in this case when you're calculating the constants of integration, you'll actually need to solve simultaneous equations. And that's because in this particular beam configuration, it's just that the left-hand reaction is not at the left-hand end of the beam in this case. So constant C2 will not be 0 as it's been in the previous questions. So you'll generate one equation at the boundary condition for the first reaction in terms of C1 and C2. and another equation for the boundary condition at the second reaction in terms of C1 and C2, and you'll solve them simultaneously to find the constant C1 and C2. So a slight added complication in this particular case. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, but I will work through the full solution on the following slides. Exercise 5M, here's the beginning of the solution. Again, notice that my elastic modulus will be used as 205 times 10 to the 6 kilonewtons per meter squared, because I'm working my calculation through in kilonewtons. Again, all the loading, the point loads applied are in kilonewtons, and the UDLs are stated kilonewtons per meter. And we're given the UB section 686 by 254 by 140 kilograms per meter from BS4 on the previous slide. So the I value from the table on the previous slide was quoted as 136,276, and that's centimeters to the 4. So again, I'm using a unity bracket here to convert that into meters to the 4. So my unity bracket is 1 meter over 100 centimeters. That's raised to the power of 4 because I'm converting from centimeters to the 4 to meters to the 4. And evaluating, that's 0.00136276 meters to the 4. Again, for convenience of the calculations, I'll work out flexural stiffness EI. So that's 205 times 10 to the 6 from above here, multiplied by the I value from above. So that evaluates to 279,354 kilonewton meters squared for our flexural stiffness value. Exercise 5M, solution continue. We need to calculate the reactions. Notice how I've labelled my beam in this particular case. I've got A at the left-hand end. I've got a reaction, I've labelled it B here, and a reaction labelled it E here. So in this particular instance, using the notation given, I need to calculate beam reaction RB, which will be this reaction here, and also RE, which will be this reaction here. I'm going to summate moments about the left-hand reaction, the RB in this case. I'm going to say clockwise moments are positive, so summation of all the moments must equal to 0 for equilibrium. So considering my beam, clockwise moments would be 100 kilonewtons multiplied by 2 meters, so 100 times 2. I add that to 300 kilonewtons times 6 meters, 2 plus 4 is 6, so add 300 times 6. 500 kilonewtons multiplied by 12, so add 500 times 12, that's 12 meters, 2 plus 4 plus 4 plus 2 is 12 meters. And I have my UDL here, and consider my UDL is 150 kilonewtons per meter. That actually spans over 8 meters, so 150 multiplied by 8, that's the total force. And the midspan of that force will be actually above reaction E here, it will be halfway along the UDL, so it will be actually at this location here. And that will be 10 meters away from B. So that's why I'm multiplying by 10. That's where the 10 comes from. It's positive because, of course, that's producing a clockwise moment about RB. In the anti-clockwise sense, we'll have RE multiplied by 10 meters, so minus RE times 10. And I've also considered the UDL of 100 kilonewtons per meter, but it's actually quite pointless here because if you consider the central location of that loading, it will actually be directly above the reaction point because the UDL spans 4 meters, so halfway along that span would be 2, and that's exactly the location from the left-hand end of where reaction RB is. So that force goes straight through the reaction, doesn't generate any moment because there's no moment arm. So that term is actually 0 in this case. I'll let you think that through in your own time, but there is no bending moment generated by the 100 kilonewtons per meter UDL in this particular case because its centroid of the UDL passes directly through reaction RB. This is reaction RB here. Evaluating, we find the right-hand reaction, RE, is 2,000 kilonewtons. I'd encourage you to check that for yourself. This is reaction RE. To find reaction RB, we'll simply summate vertical forces. Upward forces are positive, So summation of all the vertical forces must equal to 0 for equilibrium. So my upward force, I've got RB up and RE, which is calculated above up, that's 2000. Down I've got the negative 100 kilonewtons, the negative 300 kilonewtons, the negative 500 kilonewtons. I have my 100 kilonewtons per meter UDL, which is applicable here, multiplied by 4 meters, it spans over 4 meters, that's coming down, so that's negative. And I have my 150 kilonewtons per meter, that's multiplied by 8 meters, it runs over 8 meters. So that's a negative value in the equation, 150 multiplied by 8. Evaluating left-hand reaction, RB, that's 500 kilonewtons. Again, I'd encourage you to check the calculations. Exercise 5, solution continued. Just adding my reactions now to the beam. The left-hand reaction was 500 kilonewtons and the right-hand reaction is 2000 kilonewtons. So we need both of those this time when generating the moment equation. So, part 1 of our solution, we've got to find the differential equations for the moment, for the slope, and for the deflection. So, moment equation, note I'm using the notation y double dash is equal to d2y by dx squared here. And as usual, the x dimension commences from the left-hand end of the beam. So, generating the moment equation, we have negative EI y double dash is equal to, notice in this particular beam configuration, the UDL actually overhangs the reaction of 500 kilonewtons here, so I've got 100 kilonewtons per meter overhanging. So the first term in my bending moment equation will be the 100 times x multiplied by x upon 2 will simulate that UDL, so that will give me the negative because it's trying to hog the beam. The UDL is trying to hog the beam into this shape. So negative 100 x multiplied by x upon 2, and that will give us 100x squared upon 2. Next consideration for the moment will be the 500 kilonewtons, but that doesn't come into effect until we're 2 meters into the beam. So that'll be 500 multiplied by x minus 2. That's a positive bending moment because, of course, that 500 kilonewtons is trying to do this to the beam. Then we have 100 kilonewtons applied to the beam here. That produces a negative bending moment on the beam again. So that's negative 100, and that's multiplied by, in the square brackets, x minus 4. Because of 4 meters into the beam before we see the 100 kilonewtons. If I next consider the 300 kilonewtons, then that doesn't commence until we're 8 meters into the beam from the left-hand end. So that will be negative 300 and in brackets x minus 8. We're 8 meters into the beam before we see that force. Next, I'm going to consider the UDL of 150 kilonewtons per meter. Again, that's a negative effect on the bending moment. So that will be negative 150 multiplied by x minus 8 multiplied by x minus 8 divided by 2. So that's where I get the x minus 8 squared from, divided by 2. Then I've got my 2000 kilonewton reaction. That's a positive bending moment on the beam, but that doesn't commence until we're 12 meters in from the left-hand end. So positive 2000 multiplied by x minus 12 in the brackets. And then my 500 kilonewtons force, that doesn't commence until we're 14 meters into the beam for the left-hand end. So that's negative 500 multiplied by in brackets x minus 14. There is one term here I haven't considered. This is the positive 100 multiplied by x minus 4 squared upon 2. Now this is actually the compensating load to the first term in the series. The first term in the series assumes that that UDL of 100 kilonewtons per meter actually runs across the entire length of the beam, which obviously it doesn't. So what we have to do is add the compensating load that we mentioned in our previous presentation. It's equal and opposite to the imaginary loads. So the imaginary load here would be running all the way along the beam, right the way to the right hand end, which of course it doesn't do. It stops after 4 meters. So that's why we need the compensating load, which is equal and opposite. I'll show it at the underside of the beam. But this only commences when we're 4 meters into the beam. So the compensating UDL is a positive 100, and it doesn't start until we're 4 meters in the beam, so it's x minus 4 all squared divided by 2. If it helps you to think of the UDLs in this form, the negative 100x squared upon 2 is formed by negative 100x multiplied by x upon 2, and this positive 100x minus 4 all squared divided by 2 is formed by 100x minus 4 multiplied by x minus 4 upon 2. Don't forget, a moment is a force multiplied by a distance. So for UDLs, it's the UDL times the distance and then multiplied by half the distance in this particular case. I'd encourage you just to think through how we generated that first line. All that's happened on the next line is we just try to simplify some of the terms. The first term here, the negative 100 divided by 2, that simplifies to negative 50, so negative 50x squared. And also this term here, the 150 divided by 2 here, that simplifies to the 75. All the other terms remain the same. So I've called that equation 1, the bending equation. Exercise 5 continued. Just repeated equation 1 for convenience here. And what we're going to do now is integrate to find the slope equation. Just notice again the shorthand notation y dash is dy by dx. So on the left hand side I get negative ei y dash. And all I'm going to do now is integrate each of the terms with respect to x in our standard integration process. This time I will let you work through the integration process. Don't forget to add the constant c1 of course at the end. And see if you can simplify the terms to form equation 2, which is the slope equation. And then we integrate once more, this time to find the deflection equation where y is the deflection. So again, I will let you consider the integration process here. You're integrating now equation 2 with respect to x. Don't forget to integrate the constant c1, that becomes c1x, and to add a second constant term because we're integrating for the second time. Hopefully you should end up with the equation 3, which is our deflection equation. I would encourage you to start the presentation and work through that slide so you fully understand how equations 2 and 3 have been derived. Exercise 5M, solution continued. Just repeated equation 3 from the previous slide for convenience. We need to look for boundary conditions as always with these problems. So back to our beam. So looking for our boundary condition when x is equal to 2 meters in from the left hand end, we have 0 deflection. And when x is equal to 12 meters in from the left hand end, we'll have 0 deflection. So those are our two boundary conditions. So when x is equal to 2, y is equal to 0. When x is equal to 12, y is equal to 0. Called them equations 4 and 5 respectively. If we now substitute equation 4 into 3 above, so wherever we see an x, we will now put the value of 2. So there will be a value of 2 go into all these x locations in our equation. But don't forget, because we're using step functions, wherever a bracket becomes a 0 or negative value, we would ignore that bracket. So putting the value of 2 now into equation 3, we can see immediately that some of the square brackets will become negative, and so they'll be ignored. I'll let you do the evaluation. You should find that C2 is 66.6 recurring minus 2C1, equation 6. So in this particular case, we have two unknowns in one equation, and that means we'll need to generate another equation to solve. But we have one more boundary condition, so we can do that. In our previous work, the C2 was 0, but because of this particular configuration of the beam, that's not the case. So we need to evaluate both constants C1 and C2 for this particular beam. Example 5M continues. So our second boundary condition, x is equal to 12 meters, y is equal to 0. So this time we're going to put the equation 5, or the boundary condition labelled 5, into equation 3. So on the left-hand side of the equation we'll get 0, of course, because y is equal to 0. And then we put 12 into all our brackets of equation 3. Wherever we see an x, we put a 12. And notice this time only two brackets disappear. This bracket here, because we have 0 inside the bracket, and this bracket here, because it's negative inside the bracket. And simplifying the above terms, we find we get an equation of 0 equals to 666.6 recurring plus 12C1 plus C2. Call that equation 7 here. All I do now is solve simultaneously. I'm going to substitute equation 6 from the previous slide into equation 7. So C2 is going to be replaced with the C2 from the previous slide. So equation 6 here, as we labelled it. From where we can evaluate constant C1, it's negative 73.3 recurring. Exercise 5 continued. And if we back substitute the value of C1 into equation 6 we formed previously, so this is the value of C1, it's a negative value, we can find the value of C2, which is 213.3 recurring. So we now have our particular solutions that are termed for our slope equation, because we've added the C1 constant into the equation. Call that equation 2a for reference. And we've got the particular solution for the deflection equation, where we have the C1 times x, and now the C2 from above. Call that equation 3a. So those are equations that we formed. Exercise 5m continues. So now it's all about finding the slopes and the deflections as per the question. So we have to find the slope at the left-hand end. That's when x is equal to 0. So using equation 2a from the previous slide, we simply put a value of 0 wherever we have an x, and we ignore the square brackets wherever we have a negative value inside them. So the equation simplifies to negative EIY dash is equal to the negative 73.3 recurring. Rearranging for y dash, don't forget y dash is the slope. We find that's the 73.3 recurring divided by our EI, which we calculated previously, of 279,354. That gives us a value in terms of radians, which I've converted also into degrees. So a very small rotational angle, 0.015 degrees. Exercise 5m, we've now got to find the slope when the x value is 10 meters from the left-hand end. So we simply put the value of 10 wherever we see an x in our equation 2a, and ignore terms where the square brackets have negative values. Let you wander through the evaluation here, but we should find that the slope at 10 meters in for left-hand end is negative 0.053 degrees. A very small slope here, but it's a negative slope. Exercise 5m continue. We've got to find the slope at the right hand end of the beam. That's when x is equal to 16 meters, so right up this end here. So again, it's just a question of putting 16 into the equation where we have an x. So it's equation 2a again from our previous slide. Just put the value of 16. All the terms will be live this time. So evaluating, we find that the slope at the end will be 1.05 degrees. So at this end here, and it's a positive gradient here. Exercise 5m continue. This is part 2 now. We're going to find deflections at the left-hand end of the beam when x equal to 0. So now we're using equation 3a from our previous slide. This equation here. And we put the value of x equals 0 into the equation 3a. And again, as always, we ignore terms where the value inside the square brackets becomes 0 or negative. So in this case, on the right hand side of the equation, all the terms effectively disappear except for the constant C2. And from there we can determine the value of y, and that's actually negative 0.8 millimeters. Negative means it's actually going upwards at the left hand end. That may be reasonable considering the beam geometry and loading configuration. Exercise 5 continued. We're calculating the deflection when x equal to 10 meters in from the left-hand end. So again, using equation 3a, put the value of 10 into the equation wherever we see an x. And again, ignore terms that have square brackets of 0 or negative values. Let you go through the number crunching. The deflection at 10 meters in from the left-hand end is negative 6.4 millimeters. Again, negative is up. Exercise 5M continue. We're finding deflection now at the right hand end. That's when x is equal to 16 meters. Just put the value of 16 into our equation 3a as labelled. All the terms again will be live here, so we need to consider all the terms. That produces a deflection value of 65.5 millimeters, and that's downwards. Exercise 5M continued. Now we're told in the question that the permissible deflection, allowable deflection, is the span divided by 200. The span in this case between the supports is 10 meters, so 10 divided by 200. The maximum deflection we're allowed for the beam is actually 0.05 meters or 50 millimeters. We know from our previous calculation we have a maximum deflection of 65.5 millimeters, and that is actually at the right hand end. But that's the maximum deflection on the beam. So what we're going to do now is determine the actual I value required to ensure that the maximum deflection is limited to 50 millimeters. So we're going to make the assumption that EIY is constant for the current beam and for the new beam. So in other words, EIY for the new beam will be the same as EIY for the original beam we've analysed. And assuming the beam is homogeneous, then that means the E's are the same for both beams. So the deflection of the new beam multiplied by the I value for the new beam, we're going to assume is the deflection of the old beam multiplied by the I value for the old beam. So from this equation, we can determine the minimum required second moment of area. So the I value we require, the new I value, can be found by factoring the original I value by the ratio of the original deflection over the new or the required deflection. So original deflection we calculated, the maximum deflection was 65.5 millimeters. We're limited to 50 from the above calculation. So basically we're factoring up the original I value to find the minimum I value required to restrict our deflection to 50 millimeters. And that's going to be 178,522 centimeters to the 4. Remember the I values that are stated in table on BS4 are in centimeters to the 4. So that's the minimum I value we can use. So referring back to our table of universal beams in BS4, the value of 178,522 in this column here would seem to require us to use this value as the closest value. So that will be a 72 times 267 times 173 kilograms per meter beam. So referring to the extract from BS4, the smallest universal beam section we can use is 762 by 267 by 173 kilograms per meter. From the table, that gave a second area moment, an IX value of 205,177 centimeters to the 4, and if we convert that to meters, that'd be 0.00205,177 meters to the 4. We can now work out the actual maximum deflection using this beam by simply factoring the original deflection by the ratio of the second area moments. So the new or the actual deflection would be the original I divided by the new I we've just chosen multiplied by the original deflection. So the original I was 136,276 centimeters to the 4. We've just determined above our new I value for our chosen beam is 205,177 centimeters to the 4. We multiply that by the original deflection, which was 65.5 millimeters. So the maximum deflection of our beam using the new beam section above would be 43.5 millimeters, and that would now be acceptable. That would be under the 50 millimeters that the codes of practice would suggest we limit our beam deflection to. Exercise 6 I will leave with you. A simply supported beam is loaded as shown in the sketch. We have a 70 kilonewton load applied downwards at the left hand end. We have a 100 kilonewton load applied upwards, 3.5 meters in for the left hand end. We have a UDL applied of 20 kilonewtons per meter at the very end of the beam. And we're given the reactions in this particular case the left-hand reaction is 29.5 kilonewtons going upwards, and we're actually informed that the right-hand reaction here is 29.5 kilonewtons, but it's going downwards in this case. We need to account for that direction in our bending moment calculations. We're given the Young's modulus is 205 gigapascals, and the beam section is actually a rectangular hollow section here of 450 by 250 by 10 millimeters thick RHS, and that's to the appropriate British standard. We're asked to determine, part 1, the slopes or the gradients at both ends and under the 100 kilonewton load. So we need to know the slope at the left hand end when x equals 0. We need to know the slope at the right hand end when x equals 7.5 meters, and under the 100 kilonewton load, which is 3.5 meters in from the left hand end. Part 2, we've got to find the deflections again at both ends and under the 100 kilonewton load. Part 3, if the permissible deflection is 25 millimeters, so we're given the allowable deflection this time, we've got to calculate the smallest rectangular hollow section that can be used as a beam section. As with always, the self-weight of the beam can be ignored in the calculation as it's deemed negligible. Answers are shown at the bottom of the slide. On the next slide, I'll show you the properties from the British Standard. So this is a rectangular hollow section, RHS sections. In the question, we're given the section is a 450 by 250 by 10 millimeter thick section. So the I value we will read is from this column here. The moment of inertia is the I value. Again, we will be assuming we're bending about the stiffest axis of the beam, so that's the XX axis. I'm reading the moment of inertia, it's 37,180, and that's centimeters to the 4. So that's the I value we'll need to convert into meters. So I would encourage you now to stop the presentation and attempt this question. In this particular question, you do not need to find the reactions, they are given, but just notice that the right hand reaction is actually down this time, not up. Conventionally always up, but it's down in this case. So we can work out the bending expression. Notice that we start from the left hand end when x equals to 0. It will start off with 70 multiplied by x, and that will be a negative bending moment to begin with. I suggest you generate the bending equations and then integrate to find the slope and the deflection equation. You have boundary conditions here because, again, you know that the reactions here and here, there'll be no deflections. So that's our boundary conditions. From that, you can find the constants, and then you can find the particular solution equations, and you can solve for slopes and deflections wherever you want to. The answers are shown in the brackets at the bottom of the slide. Just notice that this slope should be negative 0.246 degrees. I will leave you with some tutorial questions to attempt. It's question 1. We're asked to calculate the central deflection for the simply supported beam shown on the right hand side. This is a very similar beam configurations that we looked at in a previous exercise, but I'll let you read the question at your own pace. The answers are shown in the brackets here. To answer the question in full, you'll need to make reference to this rectangular hollow section table, as you'll need to choose an appropriate RHS section to comply with the allowable deflection as stated in the question. And also question 2 for you to attempt at your own pace. You've got to calculate the central or mid-span deflection for the beam shown. The downward deflection is shown here in the brackets. I hope this presentation has been of use to you, and thank you for viewing.